Okay, hi everyone. My name is Rehan. So over the summer this year, I worked at Red Hat, and my project was auto-tuning vLLM. I was a software engineer intern at Red Hat. So a bit about me before I go into my project. I am a senior at BU. Well, a couple personal interests is I do play tennis, I ski, soccer, and my manager was Ashish Karma at Red Hat, and my mentor, if you do know him, is the meme. So auto tuning, my project. So, what was the problem? The problem was that LLM inference speed and cost can vary wildly with the configuration choices you choose, and the default settings can often provide or may often not provide you the most optimal performance. Therefore, the task that I was provided with was to find the most optimal settings for running LLM inference that can deliver the most output tokens per second, which is the throughput, while keeping the latency below a kind of a baseline value. So the method that I came up with was that I created a search space across the vLLM configuration options for a specific dataset profile. This includes the couple that are right here, and I'll go into it later in a different slide. I benchmarked with GuideLLM on models such as like the Qwen3-32B, Qwen3-30B-A3B, FP8, which is a MOE model, and a Llama 3.1 AP instruct, and then logging those results, ranking trials by objective functions, and then using Optuna samplers like TPE, BoTorch, Grid Sampler, just to guide the search. So, quick reason why auto-tuning. We found auto-tuning to be pretty valuable to provide users with kind of the best performance on certain LLM models, whether that be high throughput or low latency or even both. And I can go into kind of my findings in a bit later. So how do you run my system? So the system, it's one command line. It's a Python command line. You just serve the main file. You give a bunch of flags. You give the model flag. There's a dataset flag, max seconds, prompt tokens, output tokens, and number of trials. There are three objective functions I created. You have a single objective function, which maximizes only throughput, a P95 latency function, which minimizes P95 latency, and then multi-objective function, which does both maximizing throughput while also minimizing latency. And then I also created it so there's a YAML configuration file that gives the users opportunity to enable and disable parameters or add new parameters if they would like to. And this also can help you determine which objective function you want to use. So a quick timeline of my internship before I go into the data. For the first kind of quarter of my internship, I just focused solely on research, understanding how vLLM, GuideLLM, and Optuna all work. I developed knowledge for understanding benchmarking error logs for both GuideLLM and vLLM. And all this research I created and stored into Google Sheets on every tunable parameter for vLLM. Next, I designed a skeleton framework that implemented serving vLLM, then ran a benchmark for GuideLLM, and then Optuna saved all of this data into a study so that we don't and ran multiple trials, so we don't actually have to supervise the whole kind of process. Then data analysis was the third part, where I ran multiple trials with different Optuna samplers, BoTorch and SGA2, Grid Sampler TPE, and I gathered data from different batches of parameters. And lastly, for my last couple of weeks at the internship, I replaced GuideLLM with MLPerf, and I developed a harness that utilizes multiple GPUs so that each GPU can run its own trial on an Optuna study. So before I go into the data, this is the parameter search space that I worked with. These are the different tunable parameters on the left, the given ranges that I gave it, and then the batches on the right. I'm not going to go too deep on the ranges, but pretty much the two batches that I worked with, 1 and 2, were because given the timeline, I only had 3 months. So I separated them into 2 batches just to kind of give me more time to kind of understand what each parameter was working with. So this is the first batch that I worked with on a single objective. As you can see, so I ran this, I believe it was request latency. And as you can see, the request latency was a lot higher, or the Optuna study was able to find more optimal request latency, which is that value right up there. it slowly found the set of parameters that gave you those optimal configurations. Um, and so this kind of proved that Optuna can find those optimal set of values. However, this value was not near the baseline value. Baseline was still a bit higher. So the second one I decided to try was a multi-objective function. So as you can see here, the red is throughput and the yellow is latency. Minimizing latency, maximizing throughput. So as you can see here, there are some values where the throughput is a lot higher than the baseline. Oh, by the way, the dashed lines are the baseline. But when the throughput was higher than the baseline, the latency was also seen to be higher than the latency baseline, which is not what we want. But this shows us that we can find values or find a configuration space where our throughput is higher than its baseline, and there are some where the latency is lower than the baseline, but it's not what we wanted to see. Batch two, this is one kind of sample one data that I kind of found pretty interesting. The point that I circled right there, the parameter values are on the right if you're actually interested in it. But we found that with a latency decrease of 40.7%, throughput actually was pretty high compared to the rest of them. It wasn't as high as the baseline value, but we only saw a 19% decrease from the baseline value while having that 40% decrease with latency. Now here, I decided to change the sampler to Botor's sampler, which pretty much finds the most optimal kind of configuration space, and it slowly kind of tweaks the parameters until it finds the right set of parameters. As you can see, it kind of like straightens out towards the end. Here, these values were a lot better than the previous one, where at trial 55 to 200, throughput was actually only at an 8% decrease, while latency had a 27.9% decrease. This pretty much kind of gave me the kind of confirmation that Botorch does provide us with kind of an optimal set of parameters where we can get really low latency while having a throughput just below the baseline. However, this was only with batch one. So after this, I decided to implement the batch two parameters. And well, after implementing batch two parameters, I actually saw some pretty good results. As you can see here, around like the middle towards the end, you can see that throughput is way above the baseline. It's a 35.2% increase, while the latency is 8.5% below the baseline, pretty much showing us that auto-tuning is viable, and we can find the best set of parameters while increasing the throughput while decreasing the latency. So after all of this, I decided to integrate MLPerf. MLPerf is a collection of benchmarks to evaluate machine learning performance. Next step in the project after GuideLM was I partnered with the MLPerf engineers to integrate MLPerf workloads into kind of my harness. Why did I do this? Well, I achieved a 30% boost in throughput on the Qwen models. So my next goal was to kind of see if I can get the same auto-tuning boost with Llama 3.1 on a single L40S. Here's my MLPerf analysis, the dashed line. I'm just going to go briefly through it, but the dashed line was the baseline. As you can see, all those values above those baseline were successful trials, and the best parameters are on the right, as you can see, and we got roughly a 9% increase in performance, which was the tokens per second. So current status of the project now at Red Hat. The project has since been refactored, and it's been extended to both the meme and Anya. And the team plans to leverage auto-tuning across most of their projects, making it a core capability in performance and scale initiatives. And if you're interested in the project, that is the GitHub link right there. It's on the OpenShift PSAP GitHub page, and it is so a couple internship challenges. I went over like 200 different 200 different studies with almost 50% of them kind of failing. And yeah, that's pretty much my internship work. Thank you.